Okay, in this video, we're going to check the early strength of concrete, structural concrete, in the towers, anchors, and ramp cap, which is where we have structural concrete. We'll ignore the ramp cap because this doesn't truly have a structural purpose other than having a nice flat surface for the walkway. So we're really just going to think about the anchors and the towers here. And first things first, we need to recalculate and isolate the following loads, which we have done in some of our previous sections on anchor design, on tower design, so I won't go back into that here. But as a reminder, that is the hoisting situation and our decking situation, in which we're going to have to think about the early strength of concrete. So under hoisting, we're just going to have our distributed load in that pH term to be the self-weight of the cable, and in the decking or just post-decking, we're going to have that distributed load as the full dead load. And after this, because we're filling in the abutments, we are supporting the anchors, finishing the ramp walls, things like that. The free body diagram is going to change, and there's going to be more structural support for the anchor. So when we move on with that, as well as after more amount of time, the structural concrete will have most likely reached close to or its full strength. Now, the main difference between this analysis and, like I said, the previous analyses in the anchor and tower design section is that our governing load is changed. It's not 1.2 dead load plus 1.6 live plus our earth pressure. It's just going to be this U equals, our ultimate load is 1.4 times the dead load. That is our load combination in the load reduction factor design for structural concrete. And we'll still take the full strength of concrete to be 10 megapascals. And we'll be using our 40 KSI deformed bar or rebar. And the strength the strength of the concrete will be taken as a function of time, which was given to you in an equation in the previous section. Now, the rest of the analysis follows the previous tower and anchor analyses, just with different loading. So the forces change, obviously, based on this new 1.4 dead load combination, but the same process of checks of how we calculate capacity, how we check that against what force is it experiencing is exactly the same. And we're going to continue approximating as a simply supported beam with the moment in shear diagrams as follows. Remember, that's going to be W L squared over 8, where that L term is 2.4 meters, or the distance between the supports, the ramp wall supports. And we're also just going to be performing strength checks. We won't be looking at serviceability checks. And the items we're going to check again are going to be tower moment capacity, anchor beam flexural capacity, anchor beam shear capacity, and the bearing of the cables on the anchor or the pullout. So note that the bearing of the anchor onto the ramp wall is governed by the strength of the masonry walls, remember? And that is checked in previous sections, discussing those masonry walls in the previous section in the component design unit about ramp walls. And it's also important to think about the bearing and axial capacity of the tower. This is something we don't even check at all, and we would think this would be more susceptible to failure with, lower concrete compressive strength. And what am I talking about here? I'm talking about that actual saddle from the cable forces bearing down on that concrete column. But when we look at the capacity of the tower column, you'll notice that we are so far above the required strength, even in the worst case scenario cable loading, that we haven't at this point created this new check and added to this to the suite of checks we have. If this is something you are concerned about, your DIC is concerned about, during the design process, remember to think about this, and for now, that will be on your own to create that check.